Organizers for the organizing this wonderful meeting and also for the opportunity for me to speak here. So today I would like to talk about something concerning Schur index and modularity. This is based on some old work with Wolfgang Pilas and also some work with students Yiwen Wang, Hao Tongzheng, and also Zhao Ting Yutong, and also with Pei Haoyang. So this is the outline of my talk. I will first give a brief review of the 4D 2D correspondence, and then I will talk about something about the Schur index and non-local operators and the corresponding Schur index in the presence of these operators. And also I'll talk about the modular property of the index, and also the relation with modular differential equations. So let me begin with a brief introduction and review. So the starting point of my talk would be the 4D 2D correspondence, or more precisely the SCFT VOA correspondence. And it was proposed in this paper. The starting point is 4D n equals 2 superconformal field theory, or curly T. And the statement is that for any such a theory, there's a corresponding or associated vertex operator algebra or a chiral algebra. I'll interchangeably use these two words, and I'll also denote it using this bulk V. So this algebra lives on a two-dimensional slice inside the four-dimensional space-time, and there are some special operators which are called the Schur operators living on this space, a two-dimensional slice. And these are homologic classes of certain supercharges, and they are homomorphic, and also the OPE restricted on this plane is homomorphic. And in particular, these operators are specified by certain relations among their quantum numbers. For example, the dimension, the SU2R charge, the spins, and also the U1R charge. These should satisfy certain relation. And these relations will pick out these special Schur operators. So in any such a 4D theory, you can find all these operators, and then you realize that they form a certain chiral algebra, VT, a very mysterious object. And if the four-dimensional theory carries a 4D R symmetry, then there must be a Virasoro subalgebra inside this VT. And if the 4D theory enjoys some flavor symmetry F, then the chiral algebra VT will contain a affine subalgebra. So this VT is non-trivial. It always contains some interesting elements. So this is a big area, and there has been many discussion, and there are many aspects. For example, one can study this chiral algebra and use it to understand the 4D theory, for example, the 4D Archer theory or Archer-Locus theory. And also one can study modular differential equations, defects, and modules, and they are related. And also one can study realizations of these chiral algebras using free fields. And there are many other topics that are not listed here. And for me, I will focus on one simple quantity, the Schur index. This thing counts the Schur operators. So it's defined as a supertrace over the Hilbert space with a certain operator inside the trace. And it turns out that this four-dimensional index equals the vacuum character of the associate VOA, or the associated chiral algebra. And here I will use the standard notation Q equals exponential 2 pi I tau. And B's usually are referred to the fugacities, flavor fugacities. And this F is the Cartan generalist of the flavor symmetry. This index is a very special limit of the full superconformal index. And for us, this is the key quality. The Schur index equals the vacuum module character of this mysterious algebra. So we can, if you're not familiar with this algebra, you can think of it as some group. And then for this group, there is some very special representation called the vacuum representation. And this Schur index equals the character of this module or this representation. So this index has been studied extensively. There are many ways to compute it. Here I list three major ways. For example, one can directly count the Schur operators if you have the power to do that, and you get a series expansion. And you can also use the 2D QW's formalism to compute the Schur index, or you can use localization or the zero coupling limit to compute a full Lagrangian theories. So the outcome would be an integral of this form, an integrand z, and some integration measure, which is related to the Haar measure of the gauge group. So the index is our main target. So in the contour formula, this z basically counts some free operators, and the Haar measure basically extracts some gauge invariant part from these free operators. And as the VOA themselves are also very interesting. For example, the familiar ones are the rational VOAs. For example, we know that there are finitely many irreducible representations, and we can compute the characters, and these characters enjoy very beautiful modularity. Under modular transformation, they transform among themselves with respect to a certain representation of the modular group. And also one can use the famous Volin formula to compute the fusion coefficients. So these are the familiar stories that we learn from usual CFT. In our current setting, the SCFT VOA correspondence, there are also a lot of such chiral algebra or VOA, but they are usually more complicated. For example, they are non-unitary, and they are usually non-rational. And therefore, their representation theory is more complicated. So it's under exploration. There has been some previous work. And for us, as we mentioned before, there's one simple object that we can study, the vacuum one. That's a more familiar one. But we are also interested in non-vacuum modules. So one way to study this non-vacuum representation is from 4D physics. For example, one can look at the superconformal surface defects or line operators. They are believed to be source of non-trivial modules or representations of the VT, this chiral algebra. So my goal today is simple. We would like to explore this non-vacuum module besides the simple vacuum one. And we would like to also study the modular properties of the index. And eventually I will also talk about some equations that govern this index. So we would also like to study modularity of these equations and use the modularity to constrain the chiral algebra. So let me begin with the first part, the index in itself.
Can I ask?
Yes.
So people use the index to study the black hole microstate.
Right.
Which limit for the black hole is Schur?
As far as I know, the Schur index doesn't represent or reflect the black hole state. It doesn't. It doesn't have the growth. It doesn't have enough growth. So one would like to go to.
In that case, Qiming recently had a paper discussing. It's probably Schur.
Yes, the paper was about Schur.
It's not. I asked Qiming personally. So Qiming said he tried to his Korea friends try very hard in searching for 1/8 BPS, which is the Schur limit, and at least very high dimensions have not found the black hole yet. But if there is one, it must have hidden in a very, very high dimensions.
And this, it can see, but it hasn't seen
It
yet.
hasn't seen yet.
Right. Yeah. That's the current status. Right. So we would like to compute Schur index with or without non-local operators. And there are two helpful tools. The first is some exact integration formula, and the second is the FMLDE, some differential equation that I will introduce later. And for us, the simplest playground would be the A1 series of classes and the N equals 4 super Yang. So for us, for these theories, these Lagrangian theories, the index with or without non-local operators are usually written in this form. It's some residue of certain contour integration, where inside the contour integration there's some polynomial of the integration variable, some elliptic function of the integration variable, and probably some Eisenstein series product together, multiply together behind. So this is the object that we encounter when computing Schur index with or without these non-local operators. So we need to find a way to deal with this integral. And there's one way. There's some new integration formula. In the sense, it basically extracts residues from non-isolated singularity. In our class, mathematical physics, we learned that non-isolated singularity does not have a notion of residue. But due to the presence of this elliptic function, we are forced to deal with non-isolated singularity, and essentially we need to compute a contour integral around such object. So this formula basically help us to extract a quote-unquote residue from the non-isolated singularity at the origin. And thankfully, we found some formula to do that. We don't need to go to detail, we just need to know they exist. For example, if you have an elliptic function and you perform an integral, then the result would be very simple, just the function itself plus some combination of residue at the isolated singularity and some Eisenstein series. And you can make the game more complicated. For example, you put into the integrand some more Eisenstein series, or you can also include monomials or polynomials into your integration with some Eisenstein series or with two Eisenstein series. So these are the integration formula that we use to deal with objects like this, and they will give us the Schur index in closed form. By closed form, I mean that the final expression will be some well-known function with well-studied modularity property. So we apply all these tools.
Yes. Sorry. So a technical question. So if you computed this your integral with your method,
yes,
and compare it with the result computing from JK residue, what would be the difference?
The JK residue typically will give some, I think, two-dimensional elliptic genus, and this contour integral gives the Schur index. My paper with Satoshi.
But you can still write the Schur index as a product of theta function. So
right.
You can also increasingly you can also use JK residue.
Yeah, that will give you 0,2 elliptic genus.
Right, indeed. Two methods. Yeah, one gives the Schur index in 4 dimensions. The second method gives you the elliptic genus.
Yeah, I'm curious mathematically.
I don't know. That's a very good question. So in the end, we obtain
because that difference might probe some states which somehow you drop out after
right.
application.
Yeah. Okay, that's something I wanted to study, but haven't actually done it. Right, so we apply this formula, complicated formula, and the end result is the index equals a finite expression, a finite sum of some rational functions of the flavor velocity, probably some products of theta function and some Eisenstein series. So this is the general form of the index, with or without non-local operators. And we would like to look at these expressions and extract candidates for module characters. So that's the first tool that we use, the integration formula.
Sorry, can you explain for the matrix integral?
Yes.
If you insert a defect, which part will change?
For example, if you study vortex defect, then you take a residue of the integral. You first compute the integral, you finished it, and then you take the residue. That's one way. And if you look at Google-Witten type defect, then you would set the integration variable to approach some singular point, and then you extract the residue there. Those are the two defects that I know how to deal with. And if you insert line defect, then it's easy, mostly just some polynomial or rational function inside here. Right, that's the first tool, and then the second tool is the equations, some differential equations. Let me briefly review what the modular means. So modular group usually refer to SL2Z, or in some more general classes, a congruent subgroup of the SL2Z. Here I'll just take the SL2Z for simplicity. So a modular form of weight k is roughly like a holomorphic function phi of tau, where when tau is transformed by modular group element, then the function itself will transform by a simple factor upfront. That's a modular form. And if you have a bunch of modular forms, they can form a vector values modular form. Under the modular transformation, this collection of functions will transform according to a particular finite dimensional representation of the SF2Z. So these are some special functions of tau. So in bosonic rational CFTs, we know that there are a finite number of chiral primaries, OI, and which each leads to certain characters, let's say CH prime. And then these characters usually has a well-defined unflavoring limit. Namely, the flavor fugacity can be set to 1, and you get some finite result. And usually people play with this object, a function of tau, and it turns out that these characters, as a function of tau, form a vector value modular form of weight 0. So under modular transformation, they transform among themselves with respect to a certain representation rho of the SF2Z. So this is very nice, we know the story. And with using this story, this modularity, people have proposed that the characters must satisfy certain equations, differential equations of this form. So it's a nth order differential equation with respect to the Branda cube, where this differential operator d cube is a complicated object, but in any case, it's just a nth order differential operator. It acts on Q, together with some Eisenstein series as shifts. For example, the well-known chiral algebra E8 at level 1, you study its unique character and then you find that the character satisfies a certain equation like this, a first-order differential equation. So to arrive at this equation, people use the so-called Wronskian argument to get this equation. So this Wronskian argument is a linear algebra argument that I will not go into detail here. So this unfavored MLDE is very powerful, although the equation might look very simple like this. But these equations are actually very powerful. They are used recently to constrain and classify rational unitary CFTs in many written works. But in our current setting, we are interested in non-rational cases, so there is no Wronskian argument. Because usually characters, there is no unflavoring limit, so you cannot set the b to 1. You always stuck with a character depending on tau and flavor fugacities, b1, b2, b3, and so forth. And these characters usually will have complicated modular properties that we will see later. And also, since the phi's, these coefficients, these phi's, will in general depend on the b parameters, so they are not really modular. So we don't have a Wronskian argument to arrive at simple equations like this. We have to find another way out to derive some equation that govern these characters. And that's the second mechanism, using null vectors. The idea is simple. You start with a simple VOA, chiral algebra, and then you look at the highest-way modules, M, and you would like to compute the character of this M, so you take a trace. But when you take a trace, you have the option to insert operators, like computing a one-point function of a particular operator. And you can choose the operator to be a null state M inside this trace. And being a null state, it kills the trace, so you get a 0. So you get a trace equals 0. This is called null state equation. And this equation looks useless because it tells us that something equals 0, but it turns out that it's quite powerful. The power comes from a recursion relation proposed by Zhu. This is a formula that helps us compute one-point function. So basically, if you want to compute some one-point function of a VOA, then you can use this recursion relation to simplify your trace. And the outcome would be some simpler trace. So this is a simpler trace than the left-hand side, plus some also simple trace together with some Eisenstein series. So we don't need to really know much about this equation. We just know that when you encounter a one-point function, then you could look at the literature and search for Zhu's recursion, and this recursion will spit out some results containing simpler traces and some Eisenstein series. So this is a very powerful tool. It turns out that we can use this formula by mathematician and turn this simple equation, this algebraic equation, into a differential equation. So in the end, you will get a partial differential equation that depends on Q and also the flavor viscosity B's, and hitting all the highest weight characters, and it gives 0. So all the highest weight characters must satisfy this PDE associated to the given null state. So each null state, you get a PDE, and all characters should satisfy this PDE. One simplest example would be the beta-gamma system. So in this system, we can write down a very stupid null, namely the stress tensor equals beta partial gamma minus gamma partial beta. This is actually the definition of the stress tensor. But you can take the subtraction, you get 0. So this is a very stupid null. Although it's stupid, but when you insert it into the Jule's recursion relation, it becomes powerful, it becomes a PDE of this form. So it becomes a differential equation. It constrains the character. So this is the idea. We would like to find some nulls. And it turns out that for all the VOAs inside this 2D 4D correspondence, there exists one null that is proposed by Bimra. And this null, I'll usually call it NT in a subsequent discussion. So it tells us that the stress tensor is satisfied a property called nilpotency. So for each VOA inside our concern, there exists one null at least, and it most likely leads to a certain differential equation. And of course, besides this null, there could be other nulls. So starting from this MT and other possible nulls, we would get a collection of partial differential equations that I will just call them FMLDEs, flavored modular differential equations. And all the characters that we are interested in should be a solution to these equations. So the idea to look for modular characters is to look for simultaneous solutions to all of these partial differential equations. But these equations are hard to solve, so what do? We look at physics and then find possible candidates of solutions and check them. And the way to go is to look at the non-local operators. So we can first compute the Schur index without the non-local operators, and you get something, as we mentioned before, you can get some ugly expression, a finite sum, although it looks ugly, but it's finite. It takes this form, certain etas and some thetas and some Eisenstein. We don't need to care about the detail. We just know that it's finite sum. And you can make it shorter in this form. It's some ratio of eta and theta and then some combination of Eisenstein. I'll use this green object later on. So this is the expression that we'll encounter frequently. So without any insertion, the Schur index is known in closed form. Now we would like to study in the presence of surface defects, for example, the so-called vortex surface defect. And it was proposed, for example, in Galto, Rastali, and Rosamat. And to compute the index in the presence of such defect, it's very simple. You just take a residue. So you first compute the Schur index without insertion, then you compute certain residue and you get the answer. Given that we know what this index is in closed form, we can get the vortex index in closed form. So the outcome is also very simple, just some eta over theta, some coefficients, and some green object that we just saw earlier. So we see that the vortex index looks quite identical or similar to the index without any local, any surface defect. So we look at this expression and we look for, we check whether it's a solution to the flavor modular differential equations. It turns out that they do satisfy all the known equations. So this number k denotes the vorticity of the vortex. And there are two possible choices, case even, case odd. So if you need to go into technicality, then you have to distinguish, check that when case even, it solves all the known FMODs, and when case odd, it solves the twisted version of the FMODs. but we don't need to go into that detail. We just know that vortex surface defect are solutions to the known equations. So good.
So where can we see the parameters associated with the surface defect?
That's for this type of defect. It's very simple. The parameter is the K, the vorticity.
This type.
K is the means. So vortex is like a rotation thing, right? And this K counts the winding number of your rotation of the scalar field. So when K is large, it means the vortex is sort of rotating faster.
So K is the parameter.
Yeah, parameter that characterizes your surface defect. And for this theory, there's only one number to characterize this defect. For more complicated theory, you get more numbers. But you need to specify a set of numbers, a Young diagram, that kind of thing, to specify as vortex surface defect. So that's the first type of defect one can consider. Second is the
sorry.
yes.
You can insert like a bunch of vortices.
I'm not sure if you can insert a bunch, but insert one and then you can insert bunch in the sense that if you take a classes description, then you can take different punctures to the sort of degenerate limit. I guess that's a bunch of defect.
Just to make sure, so it's just flavor flux for the global symmetry associated with the punctures. So you specify integer for each puncture, right?
Yes, in that case, yes. If you have multiple different punctures.
And then in this case, you're having some modular things, eta to some power times the Eisen series.
Yes.
So what is the, are these already modular characters?
We check them to be the case. We don't have to prove, but we check them against these equations, and they are killed by the equations. So we believe that they are certain linear combination of modular characters. We don't have the reducibility in this game. So a second type of defect one can consider is the Cook-Witten type. And in this case, the computation is relatively easier. For example, one can consider n equals 4 super mu, and we can look at the Schur index as an integral. In particular, you can look at the integrand and you study the residues of this integrand. It turns out that these integrand, the residues, are modular characters. I think this is proved in this case. So there are modular characters hidden in these vortices and Cook-Witten type defect. And also the residues of integrand also appear as elliptic genus recently in the paper with Satoshi. So that's the surface defect. We can also consider line defects by inserting a Wilson line perpendicular to the chiral algebra plane. So in this case, the computation is also simple. You just insert character into the integral, and you brute force compute this object. I will not go into detail, but let me.
What are the representations of this Wilson line?
Sorry, the R?
The representations of the Wilson line.
That would be if you have the SU2 gauge group, then you can select all the spin J representations.
For any.
Yes, for any, but some of them give 0, so I will give the result. So we focus on simplest case, the class S A1 theory. So you start with a Riemann surface, and then each tube corresponds to a great gauge group. You can turn on the Wilson lines for some chosen gauge group, for example, this one, or you can consider correlators of Wilson lines. So you just compute integrals. The result is quite, also let me mention, for n equals 4 SUN theory, there has also been extensive results in Hasta's and Okazaki's paper. And it turns out there are 2 types of Wilson line one can consider. The first is type 1 and the second is type 2. Type 2 is simple to characterize. If you cut the Wilson line, the tube that the Wilson line resides, then the Riemann surface separates into 2. That's called type 2. If it does not separate into 2, then it's called type 1. So I focus on these 2 types of Wilson line index. So the result for type 1 is quite simple. For any spin J representation, and the type 1 index is always like this one. the original index minus some product of eta over theta and some rational function in Q and B. And the result is independent of the gauge theory description, independent of the SU2 gauge group that you choose. For example, you can choose this line or this line, it gives the same result, as long as it's type 1. And also one can check that this orange object are solution to the Flavor modular differential equation. So solutions of these FMRD is also hides inside the Wilson line index. And if you have correlators, then you get also roughly the same result, same index, ratio of eta over theta, and also a rational function of Q and B. So for type 1 correlators, the result is quite simple. For type 2, the result is much more difficult, but in the end, we still are able to extract solutions to the Flavor modular differential equation. For example, this type 2 object, we get the original Schur index, some ratio of theta over thetas, and some eta over theta times Eisenstein. It turns out that these are all solutions to the differential equations. So one can go on with this game.
So what's the meaning of the subscript 1,1, semicolon 0, 3?
Right, sorry, forgot to mention that. So we look at the type 2. To characterize a type 2, you need to specify the left Riemann sphere and the right Riemann sphere. So we have two floor indices, is G1, N1, that is characterized as the left. G2, N2 is the right, so we forgot to mention. It's sitting here.
So if one of the n is 0, then it's also 0, right? The value, expected value.
You mean which one is 0?
So if n1, for example, equals 0.
You don't get 0, you get something else. You get some result. Yes, for example, if you mean this one. Yeah, you don't have anything, I think. You're right. So the bottom line is that in Wilson line, either type 1 or type 2, we seem to find solutions to the equation, partial differential equations. So I'll skip these contents. So let me now discuss some modularity. So now we have some confidence that module characters hide inside this vortex defect and line defect and so on. So we'd like to study the modular properties. As I mentioned before, for rational CFTs, the characters satisfy this very nice modular property. They mix among themselves under modular transformation. But now our situation is more difficult, so we would like to make use of our newly found closed form formula to compute the modular properties of the Schur index. So for example, in this nice example, N equals 4, superior news, the index is quite simple, just some product of thetas and some Eisenstein. Then we can look at the math literature and look for the modular properties of thetas and Eisenstein series and compute its transformation. So for example, you can see that under STS, this thing transforms into itself times a red object. And this red object happens to be the residue of the integrand that computes the original Schur index. And secondly, we realize that this red object is also a difference operator acting on the original index. So we will see that this pattern reoccurs several times. So this is for one type of theory. Second, you can look at SQ2, SQCD, and the index is also written in closed form. And we just apply the S transformation to all the ingredients. And we find out the transformation of the index gives back the index itself plus some residues. So here residue is the integrand, the residue of the integrand that computes the original index. And it's some ratio of thetas and etas, quite simple. And moreover, this you can also rewrite this transformation into some difference operator acting on the original index. So it seems that difference operator also plays some role in the transformation modular transformation. So we can play this game over and over and look at more complicated theories. For example, when the genus 1 equals 2, then you look the S transformation contains the index itself and also some difference operator acting on the index. So this pattern just repeats itself. I will not go into detail. So in the end, we find that for A1 type classes theory, the index transform under S into combination of I itself and some difference operator acting on the index, maybe with different genus. So this is a phenomenon that we don't know how to explain, why the index with lower genus will mix into the game. Okay, so that's the transformation itself, but we would like to also see if the different module characters mix into themselves under module transformation. And it turns out that yes. For example, we look at the vortex defect index that we just saw earlier, some ugly expression with this green object. So this is the defect index. And it turns out that if you start from the original index without any defect, then you can perform all kinds of modular transformation on it, and you will get a bunch of results. And this expression form a linear space called VGM, just a random name. And the claim is that all the vortex defect index sits inside this linear space. And the proof is simple. You just play with the Eisenstein series and you realize certain equalities between them. For example, it involves the bold T, which is a difference operator involving the T transformation inside the SL2Z group. So let me give a few examples. For example, for the genus 1 four-puncture theory, you get the you get the defect index with vorticity 2 equals to the original index plus the S transformation subsequent with the T transformation. So it's basically a linear combination of modular transformation of the original index. And this pattern just repeats itself on and on. So the bottom line is that all the vortex defect index and the original index sits inside one big modular orbit. So it looks a bit like the Russian case. However, the only difference is that the modular transformation of this index contains locks. And also you can see that the modular transformation of the original index contains certain difference operator acting on the original index. And it turns out that these combination, some of these combination of more difference operator acting on the index are related to the line defect. For example, if you look at the type 1 correlator of Wilson line, then the result is of this form, the original index, and the second term is a product of eta over theta and some rational function. And this object, this product of eta over theta, is actually difference operator acting on the original index. So there seems to be some deep relation between line operators, difference operator, and modular transformation going on. At the moment, we don't have physical interpretation of these relations. And also, let me also comment that this object also appeared in the elliptic genus in 2D MM equals 0,2 theory. Okay, this is just another example of line defect, which now is a type 2. And here we have the type 2 index equals the original index, and a red guy times a rational function of Q and B's, and also another red guy times some rational function of B and Q's. So we look at these red guys, and it turns out that they are also just difference operator acting on the original index. I think these are just more examples where we have also another type 2 index of a Wilson line. So now that we know something about the modular properties of the index, we can, for example, study the high temperature limit of Schur index. And basically, we just need to rewrite everything inside the Schur index in the dual variable. For example, if you start with a b, then you can go to dual variable b tilde, and tau goes to the tau tilde. We write everything in terms of tau, the tilde variable, and then expand the index in the tilde variables. And you get the high temperature behavior. So for example, if you look at the also A1 type class S theory, and the index, we know the expression in closed form. We can look at the even n cases and rewrite everything in terms of the tilde variable. And the result would be a series expansion in the dual variables. For example, you can see that the leading Q tilde power is given by this expression. It comes from this red product. And this leading expression is nothing but the well-known chaotic behavior, which gives the difference between the C4D and A4D, the two 4D central charges. And also, people also write it as the effective central charge of the 2D theory. So that's, we can look at the leading Q tilde behavior, or we can also look at all subsequent higher order terms. So for example, you can study particular models, and then you work out all the tilde expression and expand it. And this result agrees with the recent paper by Al-Tehali and friends. And also, the same game can be performed by, for other theories as well. For example, SU2, SQCD. And also we can check against this paper. And our result is of course quite general. Just plug in the numbers, you get the high temperature behavior.
So is it with defect or without?
Without. You can also do it with defect, basically the same application. This just change the, here there's a lambda, these are just numbers. Say it's like 1/12 or 1/13. Just rush the numbers, you just change the numbers. And one can also take the high temperature limit.
Modify?
Sorry?
Symptomatic behavior.
I think so. I'm not sure if the highest term will be changed. Maybe I haven't done that. So we can go to the tau goes to plus 0I limit. That's the usual high temperature limit. In the geometrical sense, the Schur index is like a S3 times S1 partition function. And taking this limit, roughly shrink the S1 radius, and you get a 3D theory. And in particular, you are expected to get a S3 partition function. So we can take our expression and perform this limit, and you automatically get some expression in terms of the flavor viscosities. And this result can be checked against known results of the S3 partition function of the 3D SU2 SQCD. And the result matches. And of course, you can also use this general formula and perform the same limit and get more general results. For other theories, for example, you can start with a genus 0 and even number of punctures, and you take the limit, you get a general result for all these. You expect that this expression will give the S3 partition function of the 3D mirror of this kind of star-shaped curve. So we have talked about the modular property of the Schur index itself, and we found that, for example, the vortex defect index sits inside the same modular orbit as the original index. So
sorry, the previous slide.
Yes.
So the A less than C, is there any particular meaning?
As far as I know, this criteria will help us to get a good 3D theory, I think, in Guyotto's classification. If this doesn't satisfy, then you get a bad theory, I think, and it's bad. So, for example, you start with a n equals 4 theory, you have a 0 equals 0 here, then the limit is singular. So you don't get anything meaningful at the moment. So now we would like to bring the modular differential equation into the game. as we just said before, Bhima-Rasali says that there's some special null always exists in this associated B of A. And also there could be additional nulls. So the module characters are constrained by several FMLDEs and also the unflavored limit. So we're separately discuss flavored version and unflavored version. Let me look at the unflavored version, which is simpler. So the equation mostly look like this, an untwisted version, an untwisted equation, just some differential operator, and phi are some modular forms, and these are just lower order differential operators. So this kind of equation is very nice in the sense that it has modularity. It's covariant under suitable modular transformation. Therefore, if you take a solution, you perform a modular transformation, you get another solution. But the question is, in our current setting, in the associated Carrier algebra, if you take the vacuum character, you perform all kinds of modular transformation, do you get all solutions to this equation? And the reason why we take only the vacuum is because we saw that the vortex defect index with even vorticity sits already inside the orbit, so we don't need to consider them separately. So it turns out that we can start with the flavored index and look for the linear space spanned by its modular orbit. And it turns out that the linear space has a stupid basis made up of this ratio and some Eisenstein series. This bold E is the green object that we saw earlier. It's a linear combination of Eisenstein series. So there's a linear space spanned by the modular orbit of the vacuum character or the Schur index without any defect. So this linear space, I will call it curly GM, VGM. And the dimension can be computed, is given by this simple formula. Max G 1, either when G is larger than 1, then you take G, and if G is 0, then you take 1. And you sum over K plus 1. Sorry, I forgot to say that this sum is in step 2. So it's sum over K equals 2, 4, 6, and so on up to this number. And also N is even. So this upper bound is even number. But we are interested in unflavored version, so we take the unflavored reduction. And this space will reduce its dimension by a certain amount. When G is 0, then it reduced by this amount. When G is larger than 0, it reduced by this amount. So you get a smaller linear space. So in the end, you get an unflavored linear space that we'll just call VGN and with a superscript 0. And the dimension is, of course, the original dimension minus the difference. And it turns out that this number equals the existing expression in Beam and Friends' paper. They have proposed that this number actually coincides with two other things. For example, it coincides with the minimal order of an unflavored differential equation, possibly with a non-zero Wronski index. And also it coincides with the number of rational initial roots of the minimal equation, but with a requirement of a zero Wronskian index. So these are vague words. Let me see some example. For example, we can look at some simple theories and work out the unflavored MLDEs. This can be just use computer and check and find. For example, for the 0.4, namely for the SU2 SQCD, the minimal MLDE you can find is at order 2. So it's an order 2 differential equation. And after unflavoring, the number in using this formula or this formula is also 2, so they're the same. So in this case, nothing very special happens. But if you look at genus 1 with 4 punctures here, genus 1 with 4 punctures, then you tell the computer to find a zero Wronskian index differential equation. Then the lowest order you can find is 10th order. However, this formula gives 8, so there's a mismatch. It turns out that you do find a order 8 differential equation, but now this equation has a non-zero Wronskian index in the sense that the highest order term here has a Eisenstein series as its coefficient. So this kind of this kind of equation has a non-zero Wronskian index. So for other cases, you can do a separate similar analysis. So this formula gives the minimal order of the MLDE, but it could have a non-zero Wronskian index. Yes.
From your formula, can you deduce a prediction on the number of ordinary modules or simple modules?
I'm not sure if this is number. Is this the number? Maybe.
Maybe if this number subtract the log solution, will give you the ordinary.
Oh, okay, yeah. If you don't like the log, then you subtract the log. I guess yes, you can start with the expression and then remove all the log solutions and you find what's remaining. I think it's possible.
So that will be the number of ordinary modules. So can
Maybe,
you do that precise?
I think so. I think it's computational game, so you can get a number, definitely. Okay, so that's the unflavored version. But more interesting thing happens in the flavored version of equations. So these are PDEs now. Just now, these are ODEs. So these are ODEs. These are ODEs. Now, F with the flavored, you need to deal with partial differential equations. And moreover, the coefficients are ugly in the sense that the coefficients in this equation are twisted Eisenstein. So they do not have nice modularity property, but instead they have quasi-modularity. So we study the modular property of these equations, and we don't have proof, but we have some observations. And the observation is that if you start with a weight k FMLDE, or this weight is basically the order of differential. So if you start with a weight k FMLDE and you perform an S transformation, then all the Eisenstein series inside this equation will of course transform, and all the differential operators will transform based on the chain rule. So you play the game, you get a complicated expression on the right. However, you can re-massage this expression and you find that the original equation will appear. Equation of lower weight also appear. So a weight k FMLDE will always transform into itself and lower weight FMLDE. And recall that each MLDE comes from a certain noun. So it seems that this thing suggests a hidden modular structure among the nodes. You start with a weight k noun and somehow performing S transformation, you give this node itself and some lower order nodes. So this is a very concrete example. If you look at the admissible Kac-Moody algebra with k equals level minus 4/3, and you work out all the nodes. For example, you'll find a F5 node state at level weight 3. And also there's a weight 4 node of this form, which happens to be an F1 descendant of this object. And also there's a stupid node given by the Sugawara condition, telling us that the stress tensor is given by a bilinear expression of the currents. So we have 3 nodes in this game. So each node can lead to a partial differential equation. You can play the modular transformation on these equations, and it turns out that you can get a web of transformation between these nodes. So the red are the nodes that we just saw earlier. There's these red guys. And also we have this red guy also has a friend. If you hit it with the zero weight current, so basically just a Lie algebra, it forms a certain representation of the SU2, a triplet. And you start with this guy, then you perform an S transformation, you will get this guy and this guy. If you start with this N33, you perform an S transformation, you get this Sugawara node. So it seems there's some hidden modular structure within the nodes. This is roughly like the, sorry, yes?
How about the T transformation?
T, for the implicit case, the T doesn't do much, so.
I assume that T transformation at diagonal.
Yeah.
If T is diagonal and S is like upper triangular, could that be a SL2Z representation?
I mean, the entire thing? I'm not sure if this thing forms a representation, because we don't have we don't have actual coefficients. So this relation is deduced from equations, and we don't actually get the relative coefficient. It's related, or it appears. Yeah, it would be good to understand what the number here means if there's a coefficient.
I think my idea is each null, in the Versor case, that each null vector actually is itself the highest weight state of some Versor representation.
Right, yes.
Yeah, I suppose here what happened may be that each null actually represents a highest weight module.
A non-simple one.
Not simple one.
Right.
But your probably your relation here is some
kind
modular
of
property of that module,
right.
Module itself, that how this module act on the S transformation decompose into different modules.
Indeed, yeah, that would be
That has to be.
yes. Right, so, and also this quasi-modularity also places some restriction on the Cairo algebra itself. But due to the time, I will not go into detail. Just say that if you start with a weight 4 equation and you requires this structure, if you require that higher weight modular differential equation goes into lower weights under modular transformation, then it places strong constraint on the root structure of the Cairo algebra and also on the level. And also these equations, the equation from the nodes also constrain the characters heavily. And also, one can also look at the MLDs, and it turns out that for the long ones, they also behave nice under shifts of the flavor gasketing. So naively, one would say that you start with a vacuum character and you can perform different shifts, and you'll get, I'm not sure the conjecture is all highest weight characters, but this is just a conjecture in some simple cases. So let me conclude with some outlook. As we saw earlier, this MT now is quite important. It appears in many different places. It would be interesting to study how much this guy controls all the null states and also the Cairo algebra itself. As we saw earlier, if you start with from this guy, perform modular transformation, you seem to get some other nulls. And together with all these nulls, you get a bunch of differential equations, and these equations will together constrain the module structure of the Cairo algebra. And also we encounter some MLDs with non-zero Wronskian index. For example, in this simple case, E8 at level 1. This equation has non-zero Wronskian index. So one question would be if we can find its physical origin and flavor it. What's the flavored version of this equation? Does it come from some nulls, for example? And also, in our current effort, we only look at weight form quasi-modularity and restrict the Cairo algebra. It would be interesting to go up in weight, for example, at weight 6 and weight 8. And given that we now have some notion of module characters, we have some help from the physics to extract module characters, and maybe we can start from the modular property and come up with certain Berlin formula for this non-rational Cairo algebra. There has been some work in this direction in affine algebra, for example, by extending the usual notion of highest weight module to relaxed highest weight module in mathematical world. And with this enlarged set of module, mathematicians are able to find Berlin formula for more general cases. I'm not sure if we can do the same game here. Okay, thank you for your time.
Questions?
Yeah, I did say for the last part, I think in the default level -2,
Right.
we have a way to construct a relaxed with module. But I'm not sure if this provides a full classification.
Yes, that's always a problem. Is it full? It's always a problem.
Yeah. It's still a lot.
Right. And as long as it produces some non-negative fusion coefficient, it's something useful, I guess.
Probably they haven't studied the fusion of this module yet, but yeah, it's
So the last page,
Yes.
For EA level 1, the flavored MLT is known
Oh,
as
okay.
the first order peak operator.
Oh, okay, I see.
I have another question. Can your flavored MLT uniquely determine the vacuum count?
In simple case, for example, in this case, if you propose a weight 4 for the modularity, then you can fix all the characters uniquely. You can compute them in series, and they are uniquely fixed by the equations appear in this modular orbit.
And it's flavored count.
Flavored, yes.
Oh, both cases. They can uniquely.
Yes, in both cases. So basically, I work out the leading term, I fix the weight of the character, and the subsequent series are completely determined by the leading term.
Oh,
But I don't have closed form for the character.
I see. Up to a constant.
Yes, up to constant, yes.
Thanks.
How about non-vacuum character?
Sorry, yes, it contains non-vacuum character. All
Can you
characters.
determine by modular difference linear differentiation to determine even non-vacuum character?
Yes, so here all character contains vacuum and
Oh, I see.
non-vacuum for this particular case.
Oh,
Yes. But for more general chiral algebra, I don't know if this is possible.
This equation is actually calculated to all directions of the compound.
oh,
Yeah, so actually, if you just start from the highest weight vector, and you can intrinsically you can construct it.
So you mentioned before that for the Schur index with surface operator and relative difference operator act on the Schur index.
Yes.
So is that way to derive that difference operator?
I mean, the difference operator itself is quite simple. Just shift the flavor velocity.
Yeah, right. But
And
can we derive?
I'm not sure if you want to derive from what.
I mean,
In my game, I just compute the module transformation and reorganize the right-hand side into difference operators.
I see, and you fix the coefficients.
Yes. I don't have a derivative from other source.
Yeah, that's a related question is can you fix from your computational correlators of this line of loop operators? Can you guess or derive the operator algebra?
For Wilson line, the operator algebra it's I guess trivial. They just cross each other. But for if in the presence of two line, the computation is much better. And in Garoto, Cordova, Garoto, and Shah's paper, they have IR formula for doing that.
What's the implication of the inhomogeneous terms in your S transformation from the point of view of 2D to the fourth Yang?
The inhomogeneous term of
the S transformation.
S transformation acting on index.
Yeah.
Oh, good question. I don't have. I'm not sure. So, for example, you start. I don't know if there's a non-answer. So the inhomogeneous term are just difference operator acting on the Schur index. So computationally, you just start with the Q deform Yang-Mills expression and hit it with a difference operator. But I don't know what the physical meaning of that thing is. It's likely some defect index written in QEMs.
That means that the signal that between the 2D envelope is not really flawed. You have some redundant extra term on the extra.
All right, because they're equal. You start with the same thing. You perform S, they of course will have inhomogeneous term.
Yeah, but
Yeah, but I'm not sure how to interpret that.
Any other questions? If not, let's thank the speaker again. So, yeah.